In part two of my conversation with Dr. Scott Walter, a robotics and simulation expert, we really got into it about Optimus. We cover a whole bunch of things about what makes Optimus really cool, the engineering compromises involved in it, and the likely ways in which Optimus is going to be constructed. If you haven't yet watched part one, we cover a lot of the basics so you can understand the discussion that goes on in this part. I'll leave a link to that in the description, and of course I will leave a link to this video at the end of that other video. So if you haven't watched it, I highly recommend that you do that. But of course, if you want to ignore me and just watch this video, well then take a look. Hey y'all, it's Dr. Know-It-All. I'm here with Scott Walter again. This is part two of a two-part video. If you want to get the back understanding of how robots work and simulation and all that important stuff, definitely check out episode one, which will be linked up here and also in the description, etc. Anyway, so we're going to go in this episode and talk specifically, now that we have a whole bunch of background, about Teslabot and what, at least what hypothetically is going to be happening, because of course, neither one of us works for Tesla, so we don't know for sure. But anyway, all right, so there we go. Take it away.
Okay, so just kind of remind everyone what we went through in the first video as we looked at some other examples of some humanoid robots that are out there. And we also did a primer on kinematics, and we brought in the scary term of polar coordinates and how transformations work from one coordinate system to another. And also how VR is probably going to be very important, being able to teach the Teslabot. And it sounds like they're doing something like that already. So I'm going to go share the screen and show once again the slide that got me all excited and AI Day. And that was this one.
Cool.
So the technical details here is that I focused here first. I saw 40, and I was trying to break down what it is, because the human models I put together usually have like 38 or 36 or something like that. And that's not including the hands. I mean, in the hands, you can start having a lot more in there. So the right. question is, where were they putting all those servos? Where were the different degrees of freedom? And fortunately, it was broken down here. So it's like, good, this tells me a lot more. So the arms is 12. That doesn't mean 12 per arm. It means both arms. So it's 6 for each arm. You have that. There's 2 at the neck. There's 2 at the torso. We'll explain that a little bit. And the legs also seem to have 6 as well. So it's spread across that. And the hands, they have 6 servos there. So again, rather interesting, because you're thinking about, wait a minute, I've got 5 fingers. Right. Why do I need 6? We're going to try to figure that out, exactly why that's the case. And then the other thing of why, the arms, interesting choice, because a lot of human models, to really get a human model accurate, you need to have 7 degrees of freedom. So right. Why did they go with that? And we're going to come into that, and we're going to walk through this one step at a time.
Can I ask
first.
one question just before we even get going? And notice the wrist, because we looked at the previous episode about how complex the wrist joint was and all those degrees of freedom, and it doesn't look like they have any electromechanical actuators at all to control the wrist in this particular model.
I think there's a good choice for that, and we'll probably go back to it when we get to the wrist section.
Cool. All right.
Which I'll try to do. And what I want to do is I want to start out simple to sort of look at how we really want to analyze everything. So I'm going to start first with the Teslabot head. And to do that, I think it might be easier if I actually stop sharing right now.
Okay.
So we kind of see ourselves on the big screen. And pretty much what's going on is that you have 2 degrees of freedom, as is mentioned right there on the neck. And the question is, what are those 2 degrees of freedom? And I suspect those 2 degrees of freedom are first like a tilt like this, or probably, and also a pan back and forth. And that's very typical that you would have.
So you're getting rid of, you don't have this motion, but that's not particularly useful.
Yeah, that's the bend. Oh, wait a minute. I mean, if you get rid of the bend, it pretty much means the Teslabot will suck at soccer. You just won't be able to get that header that you want to have. Okay. And also,
unless it's straight on. It's got
and it won't be very subtle in communicating. Like you're going to say, over there, over there, over there. It's just, So it's going to be very bad that it won't be able to take any starring roles in movies. Okay.
Right.
So
it'll have to have, it'll have to have like sarcasm, one of those little brackets,
right,
sarcasm.
exactly.
So, you know.
So what is the whole point of the head and the movement? And it's mainly because you've got these two eyes and you're moving the camera around. Right. Now, I'm assuming that the eyes are able to also move around. We don't know. We don't know if the cameras are, they're probably just fixed. I don't think they're able to pan left and right or up or down. So it might be that fixed field of view, and all they're doing is moving how they can look this way. Now, the neck is going to look very still.
They could, of course, have more than two cameras in there because it's like a kind of a blank faceplate. So you could have two far fields, two near fields, so that you would be able to see a very wide.
A lot of peripheral, so they could be both predator and prey at the same time.
Right, exactly. There you go.
The eyes in the back of their head, just like your mother.
There you go.
Oh, didn't get the spit take. I tried so hard.
You almost got it though, because I was thinking like we should rename it Mom instead of Teslabot.
Right,
so.
Right, exactly.
Eyes in the back of the head.
Okay, so and now the thing about it is the neck is going to be very stiff because when you and I kind of lean forward, we don't have a joint that we just kind of rotate. And if we do something like that, it looks very awkward. But it's going to be gimbling right about there. Up and down, but we have a neck which has a spine and it basically curves. That's how we're able to get it, and which is also the reason why we're able to do the side, and everything else. So they only have to, and that's a good choice. I mean, why do you need that additional degree of freedom?
Right.
You don't.
Yeah.
Cost, energy, everything else. So
simplicity.
Simplicity.
More things
absolutely.
to break. Yeah.
Absolutely. So, yeah. Now, of course, the question is what's the range of motion that they're going to put on these things compared to a human? So if we are a human, we stand here, and I'm just going to try to do the pan, which would be back and forth this way. If we're generous, you can say I'm going plus or minus 90. Okay, that's being really generous. Maybe
when
like
we were
plus
younger.
Or minus 80.
When I was younger.
So we can do something like that, and we can bend down much more than we can bend up. And we can do a little bit like this, but it gets kind of hard. And you want to get way back, it's hard. So you have certain degrees of freedom. The question is whether they're going to respect those or whether they're going to do more. Right. So I don't know if they're going to, make it like an owl or, that scene from The Exorcist where suddenly a head can turn all the way around.
They probably don't want to do that just not to creep people out, because if the thing suddenly turns its head around.
Exactly. But, what we're now going to move into is sort of what's the torso, because if you look at the torso, it also has 2 degrees of freedom.
Okay.
So what is going on with the torso?
Can you pop that back up again just real quick? Because I'm trying to remember where the.
Okay. Sorry. Yeah. Let me.
Because I'm trying to, in my mind, I'm trying to remember where those actuators are according to the diagram that they.
Okay. So what we're going to do is that we're going to share the screen again, because I took it down. So if we look here at the head, we can kind of see that right there looks like a joint.
You're not sharing right now.
Yes, I definitely am not sharing, because you know what you're supposed to do? You're supposed to confirm that you really want to share.
There you go.
Okay, here we go.
Okay.
All right. We got it right. So we can look here and we can see that it probably rotates right through there. So that's where the head is going to do its tilt. And we can see this vertical axis right there.
Right. And that's where it would rotate around.
And if we look at the giant AI video, you're going to see the same thing. It's kind of like a bobblehead, right around there. Except I think a bobblehead can bend back and forth, but it's pretty much the joint is right around there. So those are those 2. Now we come down to the torso. The torso also has 2, and it seems to have 2 joints down here. Okay. And we're going to have some sort of suspicions on what we think those particular joints are. Now, I suspect,
and obviously, as opposed to a human being, again, that has a spine where we can at least limitedly bend our backs. This thing is it's bending at the waist, and that's it.
Yes, exactly. So pretty much what it's going to be is we come back here a little bit more, probably adjust my camera even a bit more. What's going to happen with the torso is it's going to be able to bend forward, but it bends right at the pelvis.
Right.
And it's going to be really stiff up here.
Right.
So it's just going to bend forward like that. And then it's also going to have a twisting motion back and forth like this.
Right.
Okay. Now, if we go into the whole idea of what's happening, with this twisting motion, we have a certain amount of redundancy if you think about it. So wait a minute, if my head can go back and forth this way, why do I need to have my torso go back and forth this way? Well, for humans, it's very important. We have a lot of redundancy in how we can move our eyes around. One, we can use our eyes in the first place,
Right.
but we can move our head. But as we notice, when we get to 90 degrees, it gets pretty tough. If I want to see what's going on behind me, I've got two ways of being able to see what's going on behind me. One is I could just rotate my feet around like this.
Yeah.
Right? Okay. But if I'm walking, if I'm carrying something like this, I'm walking on down and I want to see if something's coming. I don't want to change my direction. I want to be able to still be able to look over there. And so what I might do is twist my torso, but keep my pelvis still moving forward. So I can get that additional 30 degrees or whatever sort of needed. So there's that redundancy that they're going to have. And you can say there's also a certain amount of redundancy, like, well, I can lean forward to look down. So why do I even have to do this with the head?
Right.
Well, there's two other reasons why we want to twist the torso this way and why we want to lean forward. And it has absolutely nothing to do with the head. It has everything to do with your shoulders, because you literally want to lean in.
Right. Well, and you're changing your head is not that big, so you could do this without changing your center of gravity very much. But as soon as you start leaning over your body,
basically the head joint, the reason it's there is to compensate for the fact that when you lean forward, you're screwing up the direction that your eyes are. Right. And now you have to kind of go back and compensate. So you do this compensation thing to make sure that your head is going the same way. The reason we move forward is because we want to bring our shoulders forward, and bring our shoulders forward means we can reach further out.
Right.
And then if I come back like this, you see my hands are in a different location. And sometimes we twist because, we want to get that thing up in the high cabinet. You're going ahead and do it. So it helps.
You're getting your exercise in here today, like demonstrating.
Oh yeah, exactly. Okay. Now, again, the torso does not have this. So it will not be giving exercise classes anytime soon. All right.
Right.
So it cannot do that. It can only go forward and it can only twist. And again, we don't really twist at the pelvis or the hip. We end up leaning, our whole body curves. So it's going to look very stiff. It's definitely going to look mechanical. No doubt about it.
But there is, just in terms of balance and stuff, that's going to require an interesting counter, because it's going to have to put its butt back out. So it'll have to shift its lower body, to make sure. Otherwise it's just falling straight over. So.
Yeah. So it's probably doing something like that and kicking it out. And I'm sure it will learn that. The whole balance thing is, that's very much a solved problem.
Right. Oh yeah. It's just,
and I can say that as soon as the Segway came out, I'm like, oh, it's solved.
Right.
It's what they call the inverted pendulum problem, the idea of trying to keep a pendulum upside down and a control system for that. And I remember
I was just talking about that with SpaceX. When you launch a rocket, that's what you're doing.
Yeah.
You're accelerating.
Basically, you're trying to balance it this way by going back for it. And we can do it. The people take a baseball bat or something like that, and they're able to balance it.
That would actually be, if Optimus can do that, that would be a really good trick. If it can take a finger and balance a baseball bat, that would be, or a broom.
But it already knows how to balance itself, because that's the problem.
Yeah.
Is being able to keep the human body up. And the control systems for that, I remember some graduate students that were working on it when I was at Cornell. And they were doing it using analog computers and stuff like that. And they were just able to kind of get it to work, but the stuff wasn't ready for that at that point. But now with what microprocessors could do, it's a solved problem as far as I'm concerned. Doing balance and walking.
Is it PID control? Is that what it is?
Yeah, they could be. Yeah, it might be PID.
At least
that something even more advanced. That's what we were using back then.
Yeah,
it's probably something better.
I'm showing my age, probably talking about that stuff.
Yeah, that's like, isn't that the simplest control system of them all? Yeah. So that's the head, and that's the torso. And now let's go ahead and let's move into the next one. I will stop sharing. So or actually not stop sharing. I will share again.
Yep.
So we kind of go back to that screen.
Right.
Because what we now want to do is start looking at the arm itself.
Okay.
And what's going on here in the arm.
Okay.
And we can see that we have 6 degrees of freedom per arm.
Right.
And we can look here at the shoulder. And we can see this axis right here. And you see that angle? Remember I talked about in the previous video.
Oh, yeah. So even though the arm looks like it's hanging
30.
down straight, it's a much steeper angle. Yeah.
Right. So basically what this means is that when let's say when this axis here is 0, you see this pin that's going through here, that's the second degree of freedom.
Yeah.
When that's at 0, usually, let's say the kinematic reference point or the convenient mathematical reference point is for this to be straight out like that.
Right.
So what that means is that when it's at 0, it would be like this.
Right.
Whereas when it's like this, which some people might think 0, because a lot of people, when they build these models, the first instinct is, oh, just put the arm on like that. And that ends up causing problems with the singularities that are around there. And it's not a good idea.
Right.
Kind of want to get to the point
just
where you
happens
never
to be
really reach.
Right. So this happens to be a place where often we have our arms, but not normally like this.
We don't have them like so far up like that.
Right.
Now, in the model I had, I put mine up at 45.
Right.
And I thought that was good. If I went too far, then I was taking space out kind of down below me. But it kind of turns out the other space that you're attempting to go into is in your torso, and that's a restricted area anyway. So, so you don't worry about it. So you have a decision on exactly how you mount that. And we saw giant AI is about 15 degrees. I would say that's about 30 degrees here.
Right.
And that I'd say that's a good choice. That's what I would go with. So we have an axis along here, we have an axis through here, and then we have another axis along here.
And that's the roll axis. Yeah.
So they are using a jointed model to emulate the effect of a ball joint. And our human ball joint is very different. And this
yeah, because we have a ball and socket, so we basically have one joint that does all of that, and they're able to substitute.
Exactly. Yeah. And for those of you who may not have looked at the previous video, what we're talking about again is this. And let me stop sharing for a second.
Yeah, I was going to say you should make yourself big. So
make myself big here. So once again, the idea of a ball joint is you have degrees of freedom left and right, forward and backwards in a twisting motion. Right. Now, generally in our arm, we use this a lot and this a lot, but this not so much. Right. This roll along there, and that's this third one. However, it is kind of important. It's there. And the thing about a ball joint, it's very difficult to restrict the motion of a ball joint unless you put certain mechanics in there. So it just wants to float around. And it's also very difficult to drive. I mean, coming up with a drive mechanism for a ball screw, that's why they're doing it this way. Yeah. No one really puts a ball screw.
I mean, look at with human beings, we've got massive muscles around this area, and people still pop their joints out all the time.
Yes, yes.
It's a common accident.
The way to get it to work is to actually, rather than having like little motors down there, is to have tendons that are pushing and pulling on this.
Right.
And ligaments. And that's how the human body solved the problem of, well, how do you actuate a ball joint? And so what was interesting to me looking at the giant AI is that since they were using tendons, I couldn't figure out why didn't they just put a ball joint up there? They're doing the same thing.
Right.
Except they're all follower joints. They're not servo driven. They are actually following based on the pushing and pulling. So, I mean, think of this as like a tendon right there. It's like, whoop, see, I can actuate it there. Now look at me. It's like, it's not, you have to get a second one to pull over there to kind of get it. So, using that, you could do it. But since they're doing direct drive with the servos, then they're going to use this particular model, which is the jointed model. Right. And they decided to put 3 degrees of freedom. And that was the first question I had. Are they going to have 2 joints there, or are they going to have 3? Right. And the reason for the 3 joints is that it causes what's known as the elbow redundancy. Okay. That means you can reach the same position in space, be able to move your elbow around a lot. Okay. Okay. So now think about it. Usually we have 6 degrees of freedom in space, 6 degrees of freedom on a robot. That's 1-to-1, which means your equations work. But now if you have one more variable, suddenly, wait a minute, too many equations, not enough variables in there. And so you're trying to think, okay, how is that going to work? So you have this one free variable that you can do whatever you want that allows you to get to any location in space in an infinite number of ways. And we're not aware of that subtlety. I'm going to try to show that, exactly what the elbow redundancy is here. And so if I put my hands out here, and I think you can see them, right? Yep. They're at a fixed orientation. you know, without moving my shoulders, but just by doing this with my elbow.
Right.
You see, they're kind of keeping in the same place. So that's the idea. Now, with a 6-degree of freedom robot, you can't do that. You know, once you get to there, if that's the solution for the elbow, that's it. And the reason I can do that is because I'm able to do that third axis. I'm able to roll about the shoulder. It gives me that additional axis and degree of freedom to be able to do that.
Right.
And this is going to be very important when it comes to the hands, because look what they just did is that in a normal articulated robot arm, the shoulder joints, there's only 2 axes at the shoulder. There's 1 at the elbow and there's 3 at the wrist.
Right.
We've just put 3 right here.
Yeah.
We're now down to 4.
Right.
Okay.
So, yeah.
And so that means that you take the elbow out, now you only have 2 left over.
Right.
For the wrist. So it's like, what's going on with the wrist?
Oh, okay.
So a normal articulated arm is what I call a 2-1-3. 2 in the shoulder, 1 at the elbow, 3 at the wrist. The human arm is a 3-1-3.
Okay.
Okay.
So we actually do have 7 degrees. That's how
we do have 7 because of that ball and socket joint.
Right,
I mean,
right,
a ball and socket joint has 3 axes. It's
Yeah.
really, really hard to get rid of that roll.
Right. No, and I mean
it just happens.
You got to hand it to human beings and evolution and stuff. That's a pretty cool joint to have.
Now the giant AI seems to also be a 3-1-3. There's 7 degrees of freedom because they clearly decided they wanted to put that third axis out on the wrist.
Right.
And I'm not sure why. I would tell them get rid of it because their wrist is much bulkier than it needs to be because they're trying to deal with a degree of freedom you don't really need.
Okay. So which one are you
Teslabot
giving
is
up in this
3-1-2.
case? Are you giving up the yaw or the roll?
You're giving
or
up the
pitch?
yaw.
Okay.
You're giving up the
yaw.
yaw.
Okay.
So what they're going to have is they're going to have this kind of roll right here. And we're very familiar with the rolls, what we need to open the door.
And you can actually drive that from up here in the forearm in the robot, right? I think that's where the Teslabot has a
basically it's that right there.
Right.
So so it's somewhere along here. It's rotating along the wrist.
Right.
So you have that degree of freedom. So now if you look at that and let's see how generous we can be here. This you use a lot. And if I start my hand over here to that limit, I can come around and almost get back to it.
Right.
So if we're being really generous, it's 360. It's probably more like, plus or minus 330 or 320, something like that.
Right.
It's a little bit of a strain, but it's the one that has the most motion. So you don't want to throw out a degree of freedom that has a lot of motion.
Yeah.
The next is this. This is kind of the pitch up and down.
Yeah. So it's like plus or minus 90 or so.
Again, if you're generous, almost 90 degrees, not quite, and then maybe 30 up. So it's like about a full range of 120 degrees.
Yeah.
Now, if you look at this one,
like
here,
maybe 30 each direction.
plus or minus 30. Okay.
Yeah.
Now, everyone out there, go ahead and take that and start moving it back and forth. And you will find you don't like it.
No,
you can do it, but you don't like it.
Right.
It's like your body just tells you, I don't like that. I absolutely, I don't want to do it. And as a matter of fact, that results, if we kind of look at how some people might type, you have your hands here.
And you get your
carpal
typing. Tunnel. Yeah.
Exactly. Carpal tunnel. Yeah. Think about that. People get carpal
I remember
tunnel
that with piano lessons where I would do like this and the piano teacher was like, do not do that. Yeah. because you're like, your hands are in this weird, awkward position. Yeah.
Yeah. So, you don't want to do that. So you want to be more forward. You don't want to be that. That's like, the goofy elbow thing. But if you're forward, for the most part, you just want to keep your hand like that. So if there is a certain orientation I need, because of the redundancy in the shoulder, I can always get what I need.
Right.
There is a way to get it. And the other thing is a lot of operations that you're doing. All that's important is that my hand is flat on the surface. Right. Whether my hand is like this way, that way, or that way, doesn't really matter. A lot of times it just isn't flat on the surface.
Right.
Especially if I'm carrying a box. If I'm carrying a box, it doesn't really matter whether, the orientation my hand is in. All that matters is that I'm able to apply force this way.
Right.
And, if you want to do it around like that, if you want to carry it uncomfortably, go ahead. You don't need it. Get rid of it. So that's what they did. They got rid of that degree of freedom. You don't need it. And that is a really wise choice.
3-1-2 in that case.
3-1-2.
Yeah. Okay.
312. So they, excellent decision. Excellent decision. So it's like I would have recommended that too, because I was finding also when we do this with our own model, it almost never moves.
Right.
We always come up with a little bit, but and usually with a particular position, we get goofy elbows anyways, and we're always trying to relax that to the point. So that's why and that's why I was able to solve the elbow problem, because there's kind of this heuristic in there that says something about what you want to do there, and you're limited. So you're not trying to go like plus or minus 180 degrees with that yaw. It's just a small amount. Usually you're playing with plus or minus 15 at most.
Yeah.
And then just making sure the elbows work right. So it's a very easy heuristic to get the elbows to move the way they're supposed to.
Okay.
Okay.
So pop the share back up again, just so we can see that.
Let's go back.
So
see what else there's.
I still don't see in the problem. I still don't see is that, at least in the share. I mean, I see finger actuators, but I don't see a wrist one there. Just I'm talking about this motion.
So I'm thinking, it's kind of hard to tell, but they've got a couple of things here which might be doing the roll.
Okay.
And
so that one that's kind of so maybe there's one that's actually got the attendance.
And you got to remember is I'm not sure how accurate this is.
Right.
This is an artist impression of what's going on. Right. So they probably put a bunch of things in there. So don't take it too literally.
Yeah.
I'm looking at these numbers here and saying what's going on, and pretty confident they have 3 up there.
Right.
And then we start to move on down here, et cetera. Now let's see. The next thing, they want to go to hands or legs?
Let's do legs first, because I think hands are the most complicated and interesting. So
yeah. So let's see. I think I covered everything I wanted to actually cover in the wrist. That's good. And did that from memory too. Now, so we're going to the legs. Now, human legs can also be modeled as a 7 degree of freedom, but we really only use 5.
Right.
So there's
like this motion with the hips.
Basically you have kind of 2 up here. It's a ball and socket, but I think the ligaments are set up that the last thing you want to do is this, right?
Yeah.
You see what that need? I mean, that just hurts.
Yeah, it's a little bit small in the screen sharing, but it's that rolling motion.
Yeah, let me go back and stop the share for a second.
Right.
So if you look at this model, we have what's effectively a ball and socket joint. So we can kind of do this with our legs. I mean, if you want to, everyone can spread your legs out, and you have that degree of freedom. And of course, you have this motion forward and backwards.
And even if you're not a ballerina or something, the Teslabot to be able to spread its legs out and squat down to pick up something off the ground is important.
Yes. Okay. So
lift with your legs, not your back.
So we're going to be out here, and of course we have this for being able to put the legs out. Right. And then, of course, we have this for being able to move forward.
Right.
But if the idea of me, I don't want to twist my knee. This
right.
It's just not there. So nature has figured out how to take that ball and socket that's there and say, no, you're not going to do that.
Unless you're a famous soccer player, in which case you always do that kind of weird motion with your legs.
They might have something like that. Okay, so because she does not have that, or he or it. So Teslabot will not be able to bend it like Beckham.
Right.
Okay. So no Ronaldo headers. Right. No bend it like Beckham. It's out. It's out. Okay.
The football star Optimus is just not going to be there.
Yeah. Okay. So that means we come down to the knee, and the knee is just going to be 1 degree of freedom. Right. And then we can come down to the ankle again. So the ankle. So we have now potentially 3 down at the ankle, but you're not going to have 3 at the ankle for the same reason we don't have 3 at the wrist.
Right. Yeah.
There's really no need, because if you try looking at what's going on with your feet, and it's kind of hard to do it on mine. I mean, obviously you kind of have this. This is going to be an important one.
Well, it's important to walk because you have to be able to roll off your toes. So
and you can do a little bit back and forth, which would be kind of if you want to be duck foot or pigeon toed. Moving it back in like this. And then there's like some other one. And the only time you would have that one is if you're not on a flat surface and you roll your ankle.
But it looks like that might be possible because there's like two actuators. So I'm wondering if they're allowing that sort of motion.
It's not much. The motion is very subtle, but that is probably the motion that's key to your balance.
Yeah, and, that's what I'm thinking. As soon as you step off of level ground, you need to be able to rotate your foot in that direction. But I think this direction is probably way unimportant. Right, that rolling motion.
Yes. Now let's go back to the slide for a second here, because it's kind of an important point. Is we see right in here 2 axis feet for balancing. Now I don't think those 2 axes are exclusive of the 40 here.
Gotcha.
So it's probably part of that.
Right.
So the 2 axes could actually be kind of one of the ankle joints, or maybe there's even flex, because remember your toes can kind of come in, and that is also key to balance.
Right.
And then you've got their normal motion that you would have here. So they've got a little bit that's going on here that they're kind of hiding a little bit. And of course, you do need the force feedback sensing in your foot, so you can tell whether you're balanced or whether you're walking right. So they have a total of 6 degrees of freedom. They took one away here. I think they kind of took one away from the ankle, because you really only need 2, and added one more to the foot.
Right.
And that's what's helping them do the balance.
Okay.
Again, solid choices.
Right.
Absolutely solid choices.
And again, it's back to that engineering being compromised. And it's like, you can't have everything, because it would just be too complex. Yeah, exactly. So those are the technical details on that. And now we can move on to the next one, which is going to be lots of fun. And that is going to be the, let's see if I go ahead and get my notes up here. There you go.
We want to look at the hands.
And you can't even reference your mannequin for that, because the mannequins always have those just little blocks.
Yeah. So. And also, even the human models we have in our simulation, we don't worry about the hands. We move the wrist around. We're not worried about the fingers, because that's sort of a detail most people don't need in the simulations. So I will stop the share for a second here. And what we want to do is again, look at what's going on with the hands. And it 6 degrees of freedom per hand. So the hand does not include anything going on in the wrist. This does not count as the hand.
Right.
Okay. These are the fingers that are going back and forth. And clearly I have 1 degree of freedom, 2, 3, 4, 5.
Right.
I can move them back and forth. If you look at what Giant AI did with their motion, you could see their fingers were going up and down. They could move them individually. And I assume it's for being able to do certain operations like playing the piano. You want to be able to go. Now, we have a lot of degrees of freedom. In this case, it looks like it can go back and forth, but I'm not sure what about the side to side. Okay. So live long and prosper, I don't think they'll be able to do.
Oh,
it's going to be tough, but maybe, and well, even playing the piano might be tricky, because I'm not sure if the spacing the fingers is going to be just right.
Spread its hands out.
Yeah. I got to get a couple octaves here. That's going to be tough. So So you're going to be moving around. The main thing is that there's going to be something like that, and then there's going to be this clenching motion.
Right.
So that must be that they may with one servo just close everything down.
Right.
So so the thumb might be able to come in and then bend. Now the thumb kind of has 2 degrees of freedom, but you just use 1. So you can get away with that. And that's what's going to be interesting.
You don't think something as delicate as being able to do something like that would be important? Or like that kind of thing?
Could be. So the fine motor control.
I mean, if you were going to pick up, like, let's say a screw, right? So there was a screw or a bolt or something in a bin. To be able to do that really requires very delicate motion of the thumb in one finger.
Yeah, that's going to be tricky. And that's a decision of how much they want to do. Now, if we back up for a second, what's the difference between manufacturing the way it was done before there was robots? So spot welding was done in automobile factories way before there was robots. Humans came in and they had these spot weld guns that were hanging suspended from the ceiling with cables to lighten the load, and they could go in and do everything. Then the robots came in, and the robots did the same thing, but they didn't take the human style spot welding guns, but they came up with a new breed that they could mount directly on the robot.
Right.
So while it's doing the same thing, both tools are different. So that means the robot can't use the human rated spot welding gun, and the human can't just go over to the gun that's mounted on the robot and say, I'm going to take it off and do that.
Right.
So you'll have situations like robots do drilling, but trust me, the drill on the end of the robot is not your standard Black & Decker.
Right.
It's something completely different.
Yeah.
So the idea is you want this to be able to operate in the same world that people are in,
Right.
which means you want it to use the same tools. So we don't want to have a special set of tools for robots and a special set of tools for people. It's going to be using the same thing.
Just take something like, I mean, using a screwdriver. There's a lot of dexterity involved in like putting a screwdriver in and twisting the screwdriver.
Right.
So,
and the question is whether you're going to do that. When's the last time you actually use a screwdriver to do anything major in your house?
Most of the time I just use a drill with the screwdriver head. So
yeah. And
so basically, as long as it can do this trigger action.
In manufacturing, no one uses a hammer.
Right.
No one uses a screwdriver.
Right.
Okay. If you look at carpenters and roofers and stuff like that, they're using nail guns.
Yeah, exactly.
Yes. And part of that nail gun is, when's the last time, your carpenter actually picked up a nail?
Right. Yeah. Because he
doesn't have to. It's being auto fed.
Right.
So there's already these tools out there that can do these specialized operations. So, I mean, if you're a cheapskate and you invite the Teslabot over to your house and you want it to do some stuff, and all you have is a hammer and a screwdriver, and you didn't actually go out and get the Black & Decker, all right, it's going to have a hard time dealing with that. So,
right. So what you're saying is the dexterity is we don't need the
not that key. All that's important is it can grab this.
Right.
Now, the human rated hand is kind of the holy grail of robotics, because they didn't call them hands, they always called them grippers. So there was always these designs for grippers that can do this. So there's all sorts of grippers that are really great at picking up boxes and picking up sheet metal and picking up bottles and stuff like that. But there's never like an all-in-one gripper that can do everything. And one of the biggest challenges when the grippers are first coming out is to get a gripper that could actually pick up an egg. And it just never worked. It was like the eggs were always being broken because it just didn't have the delicacy to be able to do that.
Right.
Now, there's some really neat designs out there I saw a few years ago that looked like origami that people put together. Literally, you can build it at home for a couple of bucks, where they kind of have these tendons and things would be inflated that could actually work pretty well. And they have a lot of the compliance that you would need to make sure it doesn't work, and would happen almost automatically. But that is a big challenge, to come up with a hand that can be delicate, dexterous, and at the same time be able to deliver the force you need.
But what you're saying is, for a factory robot, it doesn't need that level. Like, basically, if it can grip something, and especially, I guess, if the trigger finger can work so it can operate some sort of a power tool.
Exactly. So it'd probably be enough. And they may be looking at it to make sure that they don't have to somehow adapt these power tools to work for it, because for some reason the ergonomics is not quite right for the robot. It's like, oh, we're going to have to get that hand to make sure it can actually grip it, go in there, and then turn the drill on and off. I don't think it's going to be one of those things where you have a special like USB port that the robot plugs into to say turn on or off. It's like, no. It's like, we don't do that as humans. The robot doesn't get to cheat. Or who knows, maybe a Bluetooth or something like that. Right. Where it will just think, turn drill on, turn drill off. It could. I mean,
that'd be pretty cool. I wish I could do that. That would be pretty neat.
Yeah. So that's so that's pretty much where the hands are going to go, and just the decisions on whether they're going to have this movement like that and then a clench.
I guess I really hadn't thought through that, but that's just brilliant. I mean, it's like, it doesn't need to replicate, because I was looking at the one that solves the Rubik's Cube, that like amazing hand that can do that.
Oh yeah.
It just doesn't need to have that kind of dexterity to be able to function. If it can do this, it can pick up a box. If it can do this, it can pick up an object.
Right.
If it can do this, it can operate a power tool. So
Yeah, exactly. So, I think we've gone through the legs, the arms, the feet, everything. So now it's sort of, what's the conclusion?
Well, it's first of all, it's got to have amazing vision, which of course is what full self-driving, autopilot, because it's got to be able to sense the world around it. So that's number one.
Right.
So it doesn't just go, flying into people or boxes or into the factory line. You just don't want to do that. So that's number one.
And I think, the sort of one of the takeaways I have is that, it won't be changing your watch battery anytime soon.
Right.
It doesn't have that level of dexterity. However, it may not be that far away, because if you think about it, your jeweler doesn't necessarily have the best dexterity either. What he has is the best tools set in the world.
Right.
So he's not trying to hold your watch going to put it down. He's got a special little vise to kind of hold it. He's got the nice little tool that goes over there to pop it out. So all those things he's able to do because he has the right toolkit. Right. So you give it the right toolkit, it might be able to do quite a bit. Now, the other thing is that I think the Teslabot will be able to remove the laundry from the dryer.
Wow, that would be nice.
I expect it should be able, because it should be pretty easy. You just kind of come in, take that pile, it's going to bring it over and drop it on the sorting table. Right. Now, it should be able to sort items like socks and underwear into different piles and potentially even sort by color. Right. Now, folding, I don't think it will be able to fold. It just doesn't have the dexterity. But I don't know whether it'll be able to take the socks and potentially do that little thing where you make the socks kind of come together. Right. And it will probably be able to pick up those piles and put them in appropriate drawers. Okay. And for a lot of people, everyone wants to say, yes, our underwear is neatly folded and everything else. However, the reality is most people, you just sort the piles anyways. Right. Just throw them and then you throw them in the drawers. At least that's the way it works in our house. So I think that's probably what it'll be able to do at first, version 1, and then it'll improve over time.
The other thing that I think, just to throw this in, is, and I don't know if it was you and I that talked about this or me and somebody else, but the idea of these Teslabots in space, on the moon, on Mars, you're not dealing with human hand dexterity. You're dealing with human hands in a really, like, a maddeningly difficult to deal with glove that's got pressure inside it. Yes. And so, it doesn't have to be that dexterous to do a better job than a human being in space.
Oh yeah, in space it'll probably be better. Much better. Yeah. So the dexterity there, I think, will definitely be improved. And now the other thing is to remember is that the human brain and the hand co-evolve together. Right. So it's really going to be, that's why I said the problem is going to be the hands and the general AI that go together. Right. And how you teach these things. And a lot of it will be taught in some sort of virtual world. So it doesn't mean like, virtual reality, they'll be putting someone on there. No, they'll be going through and just be training it again and again with these different situations. And you've probably seen, there's a good series of videos out there. I think it's called like 2-minute papers.
Oh gosh, so
good. Yes. And you remember there's like the one with the hide and seek.
Yeah. Yeah.
And it's
and how they learn how to cheat.
Yeah, exactly. How they learn how to cheat. And that's basically what's going to happen is that they're just going to take these virtual models of the Teslabot, very much like what I have, except they're just going to let it go. And it's going to go through, and they say, pick up a box and go over and do everything. Now, to do that, you're going to have really good physics in your virtual world. And the thing is, real world physics and what's going on in virtual are very, very different. Right. So you'll be able to get it up to a point, but eventually you're going to have to deploy it in a real world. Right. For it to be able to do it. Because, I mean, there's all sorts of cheats and everything that are going on with the physics and VR settings that are convincing. I mean, you look at it and you'll say, wow, that looks like how it really is, but the reality is it'll be very different. So the fine tuning, kind of chasing the nines there is going to have to be done outside of that world. But
on some basic levels, like to teach it when it sees one of those robot cars coming at it, get out of the way, or something, that kind of thing.
Or to walk, or to figure out how you pick something up.
Yeah. Or if it sees something like an oil spill, because you can, in the simulation, you can change the coefficient of friction on the ground where there's a patch of oil. Yeah. So it's like, okay, that's slippery. You might want to walk around that.
Don't get me started on the coefficient of friction, because again, they're a cheat. I mean, friction doesn't really work like that. It's a good approximation, but boy, it's a lot more complicated than you would think. So that's a good way to get started. Absolutely. Absolutely. And so, you would build some sort of intuition into it, sort of to notice, that surface looks a little bit shiny. I bet it's going to be slippery versus one that looks kind of rough where my feet aren't slipping around. Yeah. So that's going to be pretty important.
And the other thing to go all the way back to AI Day last summer, and actually this kind of cycles back to the beginning of what we were talking about, the simulation engine that they have that produces almost photorealistic simulation. So you put this virtual Teslabot in, and it's got virtual cameras, and then those are seeing this virtual world, but it looks really, really similar to the real world. And so you can, get pretty close to the actual real world. And
I think we've talked about this on Discord. So here I am going down my little tangents and rabbit holes. Is when they first started out, they had to do auto labeling. Right. Or let's say they needed manual labelers. And if you think about how difficult labeling is, and we all know what the CAPTCHA is,
and
how many times have you had a CAPTCHA in which you're not sure what the right answer is yourself? It'll say, show all the things with a boat. And you see a bunch of boats, and then you see like a seaplane. You're like, oh, is that a boat or is that not a boat? You know, the ambiguity, something like that. And what's a bus or what's a truck? And so sometimes I don't even know what the correct answer is. And they're using that to train the AI. So you have the same thing with these labelers that are going through that are looking at these frames and they're trying to identify anything. And I say it's akin to when a teacher gives a test, right? For the students, the teacher does not go through and redo the test. The teacher has an answer key. But there's always the possibility that the publisher sends out the test and they don't give the answer key. And now suddenly the teacher has to come up with the answers themselves. And sometimes the teacher might even get it wrong. And so you're assuming the labeler is getting it right. And the other thing is you don't know the information it misses. So the robot might, or you're learning something and you say, okay, I see 3 cars in there. And the labeler, like, yeah, there's 3 cars. But there's a 4th car, but the labeler missed it completely. So there can be errors of omission at the same time. And my overall feeling is that I don't know how they're quantifying the results of a labeling to say, is it really good or not? So if you bring it into a synthetic world where you're omnipotent, as I say, and it can be so realistic that no one would know the difference between it. But the thing is, I know exactly where everything is. I know the answer to everything. And if the auto labeler misses a car, I will know that it missed a car. And if it gets the position of the car off just a little bit, or if it gets the size of it off a little bit, or if it labels it completely wrong, you know, if it's supposed to be a traffic cone versus a trash can or something like that, it's getting it wrong. So the human labelers are going to get that wrong. And I almost wonder the fact that they get rid of so many manual labelers might be is that they're doing that. They have the synthetic world that is so good and is creating so much of it that that's the best way to test the auto labeler, because you know the answer ahead of time.
And there, what it indicates to me is that the auto labeler is now so good that it rarely makes a mistake when it labels real world data, that they've trained it up so well.
So good. And at that point, you have to then go into this other world where you can just start throwing anything you want at it. So you just keep on randomizing. You keep on showing the same intersection with different cars every time, different times a day, whether it's dark, whether it's raining, whether it's snowing. You know, you can have the everything wet, and then suddenly the sun is up and you get reflections. And the thing is that a car or is that a reflection? You know, all these different things, you'll be able to tell when it's wrong, why it's wrong, and you can do it so fast. Whereas if you have a man in the loop,
it's slow.
It's going to be slow and error prone prone.
And I always go back to the fact that full self-driving is so much harder than a Teslabot working in a factory, because the lighting conditions are generally the same. The floor is generally flat.
It's a structured environment.
It's a structured environment. You don't have these things where you're going up a hill in the rain with the sun shining through and reflecting off, you know, the water puddles, and that's hard. That's way harder than walking around in a factory where the lighting conditions are pretty uniform.
It doesn't rain, it doesn't snow inside the factory.
And you know, you're only moving a few meters, like a couple of meters per second, as opposed to, you know, dozens.
Yes. So everything is more structured, much easier to use. And so, you know, one of the conclusions I have is that the Teslabot is really designed for automotive production lines.
I
mean, that's why Tesla,
at least version 1.
They're not building it for small assembly. You know, when you look at the giant AI, they're thinking of other manufacturing environments. Like if you look how like the iPhone is put together in China, these long lines, and everyone's just sitting there for 8 hours a day, just doing the same thing. The Teslabot's not really designed for that. They're designed to do what you would typically see on an automotive line, and that's much larger parts that you're moving around. At first,
and the ability to move through space, as opposed to the ones from giant AI where they're like locked in place. So,
yes. Now, the advantage that giant AI had is that they can actually plug into a power source, and you don't have to worry about recharging. But I think Tesla's pretty good at batteries, so.
But the other thing is, you know, again, one of the benefits of a factory is it's got electrical outlets. I mean, literally, this thing could have a cord that's on a retractable thing. It can pull it out, plug it into the wall. Every time the battery gets 10%, it just plugs itself in. So
who knows? I mean,
yeah.
they could also do like inductive charging and stuff like that. As it's walking from here to there, is getting a charge along the way. Who knows?
Yeah.
I mean, they're already talking about trying to do that for cars. I think somewhere in Michigan, they're setting something up like that.
Yeah.
A test mile, whereas you drive over with an EV, you might actually get a boost.
Right. Well, you can think about that. Like, let's say the Teslabot's primary job is to stand at some sort of conveyor belt and put parts together, but once in a while it has to go over here. You could just put an inductive plate under the part where it's standing normally. And it's being
there's usually a lot of times you have these mats on the floor anyways for people. And a lot of times those mats are there also for safety purposes, because it tells the system that a person is standing here. They're in a safe position. And if you go off the mat, bam, everything shuts down. It's like, whoa, wait a minute. I'm not expecting them to be gone.
Right.
So those things could be turned into, like you say, like some sort of inductive charging that they just, while they're standing there, they're getting a big charge through their feet. So I think there's all sorts of clever ways to get around that. Because again, Atlas is always evidently supposed to be like out in the middle of the woods doing something.
Right. And it requires an immense amount. And also, I guess if you're thinking about military application where you have no idea the next time it's going to get charged up. So it's got to be able to go 12 hours before it needs to charge. This thing, if it can go an hour, it's probably, that's already a huge advantage. And it's walking really slowly. The actuators are smaller because it doesn't have to pick up heavy objects or run. So it makes sense that it could maybe do, I would imagine the target is probably like 8 hours, like on a charge.
Could be,
just because that would be kind of a normal shift. And
a lot of mobile robots are able to do that already, and they're carrying pretty heavy loads. They're usually able to go 8 hours.
Yeah.
Now, I think at first, I mean, do you have siblings?
Yeah.
Were you the oldest or the youngest?
I'm the oldest.
Okay, so I was the youngest, and hence whenever there was any sort of project going on, I was called the gopher.
Right.
And we all know what the gopher is. It's like, Scott, go for this thing, go for that thing, So I was always like having to pick things up and bring them to my brothers, and they would assemble it and get it all together. So I think at first the Teslabot is going to be a gopher. And it's going to be gathering parts and bringing them into where they're needed. And it's going to probably be doing like loading and unloading, like we showed in the first video where the operator is picking up some sort of automotive component and then loading it in a station and bringing a couple other components in there. That's very easy assembly. That's not hard to do. It's not delicate. It's just plopping a bunch of things down. And when they're there, stepping back, hitting the button for it to index around to the robot, and then the other robots, the industrial robots can then go in and do their stuff. Right. So again, they're doing this. They could be doing a similar task, so they would be able to do something like that. Now, I think another interesting observation is it all goes back to that shoulder joint, and it's going to be really interesting to find out what a natural motion looks like. Right. And this is like one of those questions. If you had one question to ask James Dama, what would it be? It would be how the AI is going to learn that, because we all know we have sort of a natural movement when we go from one place to another. Right. So if my arm, if I'm here and I say I want to go to a position like that, I have some way of going. And all I care about is what my end position is. Whether I go like this or whether I go like that, I don't matter. Doesn't really matter how you're doing that. But the way you do it is the one that feels like the most efficient to you, the one that just doesn't have that strain. It just feels kind of either doesn't tire you out or something like that.
Well, I mean, I could see, again, an AI can learn something like that, right? Because
it'll learn it, but it's going to learn it differently because its kinematics is not the same as a human.
Yes. But I'm just saying there's a loss function of how much energy did that just take and how much time did that just take.
Yes. And also,
so if you use those two things, but it might be a different motion than human.
Also, the acceleration is going around on that ball joint, because the human ball joint is very different. The way we actuate it, the human ball joint is actually, or the way we actuate is designed that in theory, a ball joint can go 360 in all directions, right? Right. The reality is it can't, because in order to have the socket that it's in, it's going to be a little bit bigger than a hemisphere in order for it to stay in, or else it's going to fall apart. So really you only have like a hemisphere, in which case, why are we like these actuators, the way this Teslabot is designed, in theory, it can reach plus or minus 360 in all directions. Right. But it's limited because it's going to self-intersect. So it's not there. Whereas what they've done is with our muscles is our muscles are not necessarily orthogonal. So the different joints that they have are pretty much perpendicular to each other.
Right.
But if you start to bring them around, kind of like when they showed the SpaceX with the heavy booster is going to end up taking the
the grid fins.
The grid fins. Okay.
Yeah. They're sort of like they're like
T-Rex arms,
degrees. Yeah. But they're like this, not 90
they went
degrees
from 90
apart.
to that because they needed more control authority in one direction than another. It doesn't mean they lost control authority somewhere else. It's like we're just not going to be as strong in that area. We're going to be stronger somewhere else. And so our muscles are pretty strong in moving in some directions and others not. Whereas this thing has maybe more strength in places where it doesn't need it. And when you need to combine them together, it's going to be lost. So the way it articulates around that shoulder is going to be very different than we are. So pretty much I'm saying, it might be able to throw a major league pitch, but it will be a unique arm motion.
Right.
It will be very, very unique because it's going to try to figure out the way it wants to go. And it might look a bit freakish when we see it. And again, it will depend whether we allow a double jointed elbow. I assume not.
Right.
But there could be a few things. So how does it learn that natural motion? It's going to look very, very different.
Okay. And these are things for people who are interested. AI Day Part 2 is coming up September 30th, is the last I heard. But Elon has said they're going to do a demo of Optimus, and these are things to look for. Like if you see that if they do a demo of it picking something up, how does it do that? Does it go like some sort of bizarre motion?
Yes. What does it do? Yeah, and that's what I want to see is that if you start comparing that to human ergonomics, what does it do a little bit differently? And how does the AI arrive at that conclusion? What is it doing to say, oh, this feels best for me? This is why I prefer it. Right. So it could start to give us also a lot of insight into human ergonomics and how we can do things a little bit better. I remember going to a Trader Joe's about a month ago, and I was watching the clerk there, and she just had this incredible motion on the way she was putting everything in the bag.
Right.
Also figured out how to open it. I'm sitting there. I was like, oh, the industrial engineer, or me is just looking at that and saying, I should be taking notes because it was just perfect. But no one else did that. They were all doing it another way when I could see, they're physically overloading themselves. They're going to get carpal tunnel because of the way you're doing it. Right. But it was just this elegant motion that was just so easy. And that wasn't obvious for some reason. But once you saw it, it's like, that's the best thing. So I'm kind of wondering with the AI, when you start to show it, okay, we're going to have the Teslabot bag groceries.
Right.
It may come up with a really cool way that after you look at it, you're going to start saying, this is how we actually teach people to do it.
Right.
Because not only was that clerk really quick and efficient, but she wasn't going to be hurting herself either. So you really solve two problems in the optimization problem that usually you're sacrificing one for the other.
Right. So I'll tell you one other thought, because I know we're being at this for an hour almost, but one other thought I've had is the digital self-management tools that Tesla has, which are the fact that the AI runs the factory and says, you're doing a good job right now, you're not, all that kind of stuff. Think about how integrated that could become with Optimus, because it can be getting real-time feedback from the main AI that's going like, you're inefficient right now. Can you shave 1/10 of a second off of this traversal? It could be doing micro adjustments that human beings just can't do. And so you might see that over time, it starts doing things that look really strange to human beings because it's plugged into the factory and it's getting real-time feedback and adjusting itself. And we might go, why is it doing that path or doing that particular motion? And then humans can look at it and kind of reverse engineer
and figure that out. Yes.
Crap, that's the best way to do this. And we never thought of doing that before.
Right. So it will probably reveal more about ourselves. That's what science fiction is about, right? And this is very much science fiction, is it's self-reflecting on what's going on. And the other conclusion is that I would design the shoulder a little bit different.
Okay.
As we've been mentioning, and the shoulder is basically like a robot wrist, except it's at the shoulder. It's almost the same kinematically. And that's usually called a spherical wrist. And like I say, the spherical wrist is designed to reach areas that mechanically you can't get to. There are other robot wrists that are typically used for painting robots, which are
Right.
actually designed in such a way that they can't come all the way back on themselves.
Okay.
I mean, they physically can't do it. So basically you're saying, oh, there's an area my wrist can't get to, but it doesn't matter because physically you can't get there. So why would I design it that way?
Right.
And they just move around really quick, and they're hollow, which
Right.
means stuff is able to go through it. So it's like, aha, that would be a great idea, because then by making the wrist hollow, or sorry, the shoulder hollow, it's a lot easier to run all your services through without them getting kinked. And plus, I think you'll get a different kind of motion around your shoulder that might emulate the human shoulder a little bit better. So that's one thing I would explore. This is version 1.0. The most important thing is they get something out. The mechanics can be fine-tuned later on.
Right.
It's the AI that is the most important thing.
And probably like the dimensions of the robot, if they can get those pretty locked down, because that means the data that they're collecting will be usable in the future. Like you don't want version 2.0 to be, 3 inches taller and 2 inches wider, because then suddenly all the data you collected is not useful anymore.
Yes.
So if they can get the basic metrics of it, the basic weight, the basic height, all of that stuff down, then the data they collect is all super useful.
Yes.
So, cool. I was just talking to Corey Steuben from Monroe Live, and he was talking about the super bottle that they had in the 2018 Tesla Model Y, and how he was like, it was absolute genius. And then 2 years later, it became the heat pump. And so they just threw away something that was groundbreaking, because it was, so I'm thinking like, Optimus version 1 is going to, so Optimus version 1, the internals of it, at least, by the time we get to Optimus version 2, it might be like, oh, this was genius. Oh, but that's old hat. There's something completely new inside it.
They learned so much along the way. It informed them on what that next step was.
Exactly.
So you're ready for it. So yeah, that's why. And that was a great interview you had with Corey.
Oh, thanks. Yeah.
And thanks for the shout out in there again.
Yeah,
so
absolutely. You deserve some of that stuff. So, all right. So I think we have been going at this for quite a while. I'm sure there will be questions in the comments and stuff. So we'll just sort of track that. And if we need to do a Q&A episode after this to like, people are like, well, what the heck did that mean? Or what about this? What about this? Then we can do something like that where we answer some viewer questions. So that'll be really
good. Yeah. I think it would be nice to be fun to do a follow-up, no doubt about it. And again, I want to say thank you to all your viewers for being so kind to me in the comments. So there's a lot.
Well, know what you're talking about here, so
yeah. I mean, it's like I was looking at the comment section; it was all very interesting, and then wondering whether I should join in there or not. Oh, the best thing is let them do it. And like there was one comment that maybe wasn't too favorable, and then to see that basically your viewers came to my rescue, so I didn't have to do anything. It's like, oh, okay.
Yes, so, I've discovered probably not getting involved in
the best thing is don't get involved. Don't feed the trolls, as they say.
Exactly.
And yes, so you've got some of the best viewers out there. So
well, thank you.
Thank you very much. And hopefully we can get at least a Gerber out of this one.
There you go. So we'll try for a Gerber or Gerber and a half.
Gerber or 2 or 3. Let's see.
We'll see how it goes. All right. Thank you again so much. And to everybody who watched both of these episodes, thank you all for sticking with it and everything. And we will see you later. All right. Bye-bye.
Bye-bye.